All right. Hi, thank you for coming. Um, I to start with, um, does everybody get access to or order the textbook? Great. Um, I will note that so one of the things for me that it's kind of difficult, like it's hard for me to sit down and read a math textbook, even though I've been at this for that many years. Um, so you one of the things I recommend is to like sit down and read it aloud. So if you've got the ebook version, you can have there's like programs that have it read it aloud to you, or in the Mac settings, there's like where is it? You can't see this. There's like accessibility and like spoken content, and you can select some text and have it read it aloud. I find that super useful. Um, if you're more of like an audio processor, that can help. Um, it sounds silly, but it kind of works. Um, I'm going to talk about that next time, I think. So I want to briefly talk about the problems that we worked on last time. I need to open Canvas for this. No, go Canvas. So let's go over the problems. Those live in modules and interesting problems. So let's briefly go over like how many games are played in the NCAA basketball tournament. So for that one, so the NCAA. So it starts with like the first four, right? First four games. And then you have, what is it, 64 teams? And so if you've got 64 teams and everyone plays each other, then that's 32 games, right? So 32 games in the first round. And then as a result of that, you have 32 teams because it's single elimination. And so 32 teams is gives you 16 for the second round, 8, and so on until you've got the final two and then 1. And so to find out how many games, you just add them all up. So 4 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. And I added this all before, and that's not 64. 67. So because we kind of need to reason of how many teams are there, how many games get played. Yeah.
Do we need the extra 64 at the start? Because like there's 64 teams at the start. Are there also 64 games?
Oh, right. Yeah. No, I think. Yeah, you're right. Thank you. Right. So because there's 4 games at the start and then 32 games are played. But we start with 64 teams. Yeah, thank you. Let's talk about the last digit. So the number is 3 to the 1776. And this looks annoyingly difficult because I don't want to multiply 3 1,776 times. But we don't need to do all of that. So how do you... So we start with... So this is a technique that we'll go over again and again, where instead of having some huge problem, we start small. And so we start with 3 to the 0. 0 is an exponent, and we know that number is 1. 3 to the 1, well, that's easy. That's 3. 3 squared is 9. 3 cubed is 27. 3 to the 4th, 81. And so I won't go into all of it, but if you continue to write out powers of 3, so for 81, we've reached a 1 again. Anyone have 3 to the 5 off the top of their head? No, that's okay. I will conjecture that it ends in a 3. Yeah, that sounds right. But it ends in a 3. And so if we keep going, we see that this cycle repeats in a pattern of 4, where we have 1, 3, 9, 7. And so we'll talk a little bit about the mod function. If you've taken some programming classes, you probably recognize the percent operator, the modulus operator. And so these two are the same thing. And so if we number one of them 0, 1, 2, and 3, then what we just have to do, this is mod 4. And so we just have to divide 1776 by 4. And this gives you the remainder. That's what we want. And so 4 goes into 17 4 times, remainder 1 goes into 17 4 times, remainder 1 goes into 16 4 times, remainder 0. That remainder tells us which number we need to pick. So the last digit of that number is 1. Okay. For hair, the hair one, the idea is that the population of San Francisco is like 800,000. The population of LA is 4 million. And when you're reading through the textbook, I find it hilarious where they're like, assume that wait, what is it? Yeah, it's like the suppose that like a human head, half of a human head is covered with hair, the radius is 6 inches, and it's assumed to be spherical. And so they use like half of the surface area equation to figure out how much of the head can have hair, and then 20 follicles per linear inch gives you around 100,000 follicles of hair on a human head. And so since that is less than 800 and it's also less than 4 million, then yeah, probably there's yeah, there's probably at least 2 residents of San Francisco and Los Angeles that have the same exact number of hairs on their head. There's also 3 to the 400 versus 4 to the 300. And so your intuitive answer might be that 400 is bigger than 300. But does 4 being 1 more mean that there's more of these guys? No. So we can reason this out without a calculator. So there's exponent rules which we'll cover a little bit today, where 3 to the 400 is the same as 3 to the 4 times 100. And similarly, 4 to the 300 is equal to 4 times 3 times 100. With exponent rules, this turns into 3 to the 4 to the 100. Because when the exponents are multiplied, this is what's actually happening. And so we can do that 4 to the 3 to the 100. And then now we just have to compare the bases. So 3 to the 4 versus 4 to the 3. This is, in my notes, 81. And this is 64. And so 81 is bigger than 64. Therefore, 3 to the 400 wins. Let's talk about ice cream. The ice cream question is where you walk into a store with 12 flavors and you have a magic cup that can stack all of the flavors. How many different ice cream cones could you choose? Assuming that the order matters. Because like if you get chocolate and vanilla chocolate over vanilla is a different experience than vanilla over chocolate. So if we have 12 possible flavors, then that means there's, at the beginning, we have 12 things to choose from, and then we have 11 things to choose from after that one, and then 10. So as I choose a scoop, I'm not going to have 2 scoops of chocolate. I'm going to have 1 scoop of chocolate, and then I want to try all the other ones. 9, 8, and so on, until we're left with only 1 flavor. And so all these get multiplied together, and we have 12 factorial. For the second problem, the second variation, what if you only wanted to choose a maximum of 3 flavors? So if I only wanted to walk out with a 3 scoop ice cream cone, I still have 12 choices to start with, right? There's still 12 flavors available. And then once I do that, then there's, nope, that's the wrong number. Then there's 11 flavors available. And then for my third scoop, I've got 10 choices. And so that, I believe, is something like 1320, whereas this is 479 million. So a lot less options. Any questions? Okay, so those are kind of fun questions to start with. Your assignment for next Friday involves like coming up with a question. So these are some fun, interesting questions. So the challenge is for you to come up with one of your own. It's a super vague prompt. That's kind of the idea, where go out in the world and maybe it's a question on like how many colors of car are there? Like how many, if these are, I'm staring out of the parking lot. So like how many variations of car colors could we fit into this small parking lot? Something like that. Okay. So to get started, we're going to talk about section 2.1 today in the textbook. And this is all about axioms, where we have to start somewhere. And so we have to lay a groundwork for the notation and different properties that we're going to talk about. So let me go to the spot. So we have to define a few things. So we're going to start with a set that we draw with this fancy what we call it Blackboard Z. So it has like the doubled parts of the crossbar. And this set we call the integers. And so the integers is just it's an infinite set. So it starts at negative infinity and it goes until like -3, -2, -1 until we get to 0. And then we start counting up. 1, 2, 3, and so on. So it's all the, so 0, 1, 2, 3, these are all whole numbers. There's no fractions or decimals. And it's positive, negative, and 0. These are the integers. From there, we can restrict it to get the, so the book does it like that. I sometimes draw it like that because I find that easier. And these are the natural numbers. And so these, it's like if we just cut the integers off at 0. And so that's 1, 2, 3, and so on. Those are the natural numbers. There's some shortcuts that we might see in the notation, where if we write a lowercase n in square brackets, that means the natural numbers up to n. So that's like 1, 2, 3, and so on until we get to n. And then the set stops. We might also see n sub 0. That's the natural numbers including 0. So we just add 0 onto the beginning. So next we've got, let's do it that way. Next we've got the Q, which is the rational numbers. We also call them just the rationals. And these are all numbers that you can write in the form of a fraction. So you can write, so we'll see it as m over n, or if you don't want to write it in like fraction form, like fancy fraction, m/n just inline. And so where we say m and n are both integers. So this is fancy notation that says m and n are in the integers. So this, when we get to LaTeX, that's \in, not epsilon, or epsilon's different. I will say that all of these, so these fancy letters, you can start in LaTeX with math, BB, and then the letter goes in there. And so this will be in math mode. We'll talk about LaTeX later, but just to let you know now that that's where we will get there. Okay, so we don't necessarily have this nice written out set like we did for natural numbers or integers for the rationals, because there's a ton of them. So we can write a rational number. Oh, I forgot one last thing. We need to not break reality. So n can't be 0. So there's a ton of different ways to write it. The representation of rational numbers is not necessarily unique. So we have the case of like 3 over 5. We could write it as like double each of the numbers by -2, -6 over -10. That's the same number. That's also the same as 60 over 100. And it's not unique. And so we could also choose to write it as a decimal format and add on as many zeros at the end as we want. So it's not unique. let's say representation. So once we've got the rational numbers, then we'll look at the real numbers. And these are numbers that we don't represent by fractions, or some of them can be fractions, but not all of them. So like 3.5 is a real number, but also like pi is a real number, but we can't represent it as a fraction. We can approximate it as a fraction, but we can't accurately write pi as a fraction. So the book says there's decimals, periodic decimals, so like 3.45, which is 3.454545, and so on. Non-periodic, they give an example of 0.101, 001, 0001, and so on, where like we increase the number of zeros. So this is not a number that we can just like write a bar over. It's more complicated than that. This is also a real number. So one of the interesting things about these sets that we're all talking about is that the ones we started with are contained in the later ones that we get. So, for example, the natural numbers are contained in the integers, right? So all of these numbers are in the integers. All of the, like, you can write the number 1 as a rational number. It's just 1 over 1. So all of the natural numbers and integers are also in the rationals. And similarly, all the rationals are in the reals. So we can say that they all belong in those sets. So we can say that the naturals are subsets of the integers, which are subsets of the rationals, which is the subset of reals. And so that's subset, which means all the elements in that set is contained in the other. So every natural is in the integers, every integer is in the set of rational numbers. In LaTeX, that's subset EQ. If you just want to say it's not equal, then it's just subset. It is possible to like construct, if you have the natural numbers, you could construct if you have the integers, you can construct the rational numbers and then the real numbers. That kind of gets into like abstract algebra territory, so we won't go over that, but it is possible and it's kind of cool. Okay. So next, let's go into the properties. So we have to kind of lay some ground rules for our work. Because in math, there's like, we don't just make everything up. We prove a lot of things, but that means we have to start from somewhere. We have to say, this is where I'm starting from, and everything else we can prove based on that. If you like calculus, the class real analysis, when I took it, it was abstract algebra, but I loved that class because we start from like sequences and we build up to make all those definitions and theorems that you learn in Calc 1 and just apply. So you have to be able to start somewhere, build it up, so you get this set of conclusions that you can work with. So we need to have some axioms. And so those are the ones in property 2.1, which are on page, what page is this? 10. And so we say, let S represent any one of the integers, the rationals, or the real numbers. So ZQR. So S is just standing in for one of those. And so we say the following properties hold for any three elements in that set. So no matter what it is. The first one is closure. So the sum, difference, and product of two numbers that are in S is also in S. So if we say like 1 and 2, those are integers. And if we add 1 and 2, we get 3. 3 is an integer. That's what that closure property is saying. And so if we add like 3/5 and 1/2, we're going to get another fraction. That fraction is also a rational number. If we add pi and e, both irrational real numbers, we're going to get another real number. So when we do these operations, closure just means we get something that's also in that same set. So there's no possibility for us to add two integers and get something that's not an integer. So that's closure. Commutative, this feels fairly straightforward and duh. Can I highlight? So that's saying that if we add two numbers, 1 and 2, that's the same as 2 plus 1. And if we multiply, 1 times 2 is 2, 2 times 1 is also 2. So they're the same. Associative laws, meaning that if I have 1 plus 2 plus 3, that's 3 plus 3, which is 6. That's the same as if I had done 1 plus 2 plus 3, which is 1 plus 5, which is 6. So I can have those parentheses either way, and it gives me the same answer. And that also holds for multiplication. Distributive law, that if I have A, then times parentheses B plus C, that's the same as AB plus AC. So if we have 1 times 2 plus 3, that's 1 times 5, which is 5. And we assume that that's the same as 1 times 2 plus 1 times 3, which is just 2 plus 3, which is 5. So this is a property that we assume will always hold for any number in our integers, rationals, or real numbers. Okay, so that's distributive. The additive and multiplicative identities just says that 0 is an additive identity, where if we add 0 to any number, we get the same number. If we multiply any number by 1, then we get the same number. Additive inverse is, we denote the additive inverse of some number as negative that number. So if we've got 1, the additive inverse of 1 is -1. If we have 500, the additive inverse is -500. And there is a multiplicative inverse for the rationals and the reals, as long as A is not 0. And we denote that multiplicative inverse as a to the -1. So we don't, so from like algebra, we know that the inverse of 3 is 1/3. We don't necessarily care about that here. We just know that if we have a number a and we want its multiplicative inverse, we say a to the -1. And so multiplying a times a to the -1, we know from algebra is a times 1 over a. The a's cancel out to 1, and then you just get 1. And then the exponential laws, this is where the 3 to the 400 problem gets its solution, where this first bit is saying that if the exponents are, we have a to the n raised to the mth power, then we can just multiply those exponents. If we have a times b to the n, we can distribute that n to each of those. So we have a to the n times b to the n. And then if we have the same base and they're raised to two different exponents, we can combine the base and add the exponents. Okay, so we're not proving these. These are just things that we're taking for granted. So with that, now we want to prove some things. Let me zoom in. So theorem 2.2 so this is also in the textbook, and the textbook has all of these, like it lays out the steps for you, and our job is to just at each step answer why. And so that why could be one of the properties of additive inverse, multiplicative inverse. 0 is the identity for addition. Or it could be, as we go on, we may use previous parts of the theorem to prove later parts of the theorem. So we're going to look at this first one, where we're trying to prove that for any real number a, so we're in the real numbers, the additive inverse of a is unique. So from the properties, the additive inverse is 0. And so we want to prove that 0 is the only additive inverse, that there's no other secret inverse that's living in the real numbers. We want to prove that 0 is one of them and there's nothing else. So if we want to prove that something is unique, the way we do that is we assume that it's not. So this is a really common proof technique where it's called contradiction, where we say, I'm trying to prove this. Let me assume that that's not true, and I work out the consequences. You work out the consequences and get to a point where that original assumption was crazy. That makes no sense. Therefore, the original statement has to be true. And I think we'll talk more about that as we go. But this is a super common proof technique. So that's why we start out with, to prove the uniqueness of the inverse, assume that B and C are both additive inverses of A. And so that's basically saying we want to prove there's only one, so let's assume there's more than one and see where it goes. So we start with B equals B plus 0. And the reason for that is this is the additive inverse, where we choose one of the ones that we're trying to prove is an inverse, and we say, obviously, B is equal to B plus 0. We're going to work things into that equation and try and get to this point. So this step comes from property property 5, the additive inverse. Yeah. I think I have to, they're on different pages, yeah. So yeah, so that's number 5 that we're looking at. Or additive identities, sorry, I got that wrong. So additive identity. And then we look at B, and then we get to a step B plus A plus C. And so in this step, we've replaced 0 with A plus C. So this is because that we assume that B and C are both additive inverses of A. So C is basically like negative A. And so this comes from the property of additive inverses, which is property 6. And then the next step is we move the parentheses around. That's the associative property. And then by our assumption that B and A are additive inverses of each other, so that's 6 as well, and by assumption. So we've assumed that B and A are additive inverses, just like here, we assumed that A and C were additive inverses. And so since these are additive inverses, then we can just replace that with 0. We have 0 plus C. And then again, by the additive identity property, we get C. And so through that, B equals C. And that means that B and C are not two different numbers. They have to be the same number. And so A must have a unique additive inverse. Okay, so the main idea is choosing which property applies to this step. So what I want you guys to do is we've got 10, 25 minutes left. So let's take a few of those, and I want you to, if you have the book, pull it out. If your neighbor does not have a book, find a neighbor who does. And I can leave these parts up too, or I can show the properties. And I want you to go through each of the steps. The book has the steps for you, and just identify at each part, which property do you use, or which part of the theorem that we've already proved do you use. So this is about finding the justification. Any questions before we get going? All right, go for it. Yeah, questions.
Like,
So, oh, I think I misread. I read the wrong problem at the beginning, but then we ended up proving it. So, start at 2 and get as far as you can. The answers are already there. You don't need to come up with why. You don't need to come up with the actual answers. You just need to come up with the reasoning. Other questions? Okay, go for it. At each step of the way, so it provides us all of the steps, and at each step of the way, we're either choosing to supply one of the properties that we assume, or we're dealing with the ramifications of the assumptions that we made. So for example, for the one of Number 4, the number 1 is the unique multiplicative identity for R. So we know that 1 is a multiplicative identity. That's one of our properties. But what we want to do is we want to assume that there's something else that behaves the way that 1 does for multiplication. And so if we assume that's the case, then we need to explore the ramifications of that. So that involves, I said number 4. So that's where we get to a step like E times A goes to A, where it's this step goes to that. And so that's where our assumption is coming into play, where we've assumed that E behaves like 1. And so because we assumed that, that's how we get from one step to the other. So it's not always we're relying on the properties, because the property is very specific to say that 1 is the multiplicative inverse. So here we're assuming something different, and then we're looking at the ramifications. I just briefly want to talk about absolute value. So you probably know the absolute value of something, like the absolute value of -2 is 2. We're defining that explicitly, where we say the absolute value of x is x if it's greater than or equal to 0, or -x if x is less than 0. Wait, what? Am I missing something? It's a negative. Oh, yeah. Thank you. Yeah. So what this is doing, so yeah, so that's where something like this happens, where if we have x equals -7, we negate it, and then that's where we get 7. Thank you for that. So we negate it if it's negative. I know we're running out of time. So absolute value is used to represent the distance between two numbers. So that's where we have the a minus b, take the absolute value, that's the same as b minus a. And that gives us the distance between a and b, regardless of whether they're greater than 0 or less than 0 or one's bigger than the other. And then there's 2 theorems that will, I want to make you aware that these exist. And tomorrow or next time, we'll briefly talk about floors. And this is one of the homework problems. So if you want to take a look at this part of the textbook, then you can start working on the first few problems of the homework. All right, thank you very much. I will see you next time.